Sogule ma'am,
Ah,
you can
yes, sir.
start.
Yes, sir. Yes, sir.
Yes,
Whether my
you
voice is
are.
audible?
Yes, yes, you can continue.
Okay, okay, sir. Good evening, one and all. I welcome you all on the third day of ATAL FDP. We will now begin our session on intelligent control systems for EV controller to be delivered by our esteemed expert speaker, Dr. Axaykumar Mehta, sir. Before we proceed with the session, let us take a moment to have a brief introduction of our expert speaker, Dr. Axaykumar Mehta. Dr. Axaykumar Mehta is a senior academic leader and distinguished researcher in electrical and computer science engineering, currently serving as professor and dean academic affairs at the Institute of Infrastructure Technology, Research and Management, Ahmedabad, India. He holds a PhD in Systems and Control Engineering from IIT Bombay and an MTech in Control System Engineering from IIT Kharagpur, with over 2 decades of experience spanning teaching, research, and higher education administration. Dr. Mehta has played a pivotal role in advancing academic governance, curriculum development, accreditation, and implementation of NEP 2020, while previously serving as Associate Dean and contributing to the establishment of several centers of excellence, including those in defense technologies, AIML, drone technology, and automation. His research expertise lies in robust distributed and AI-enabled sliding mode control for multi-agent systems with applications in autonomous vehicles, drone swarms, robotics, smart grids, and defense systems. He has authorized numerous high-impact research publications, served as organizing chair for international conferences in collaboration with agencies such as ISRO and SCRB, and held visiting academic and leadership positions in India and abroad, making him a highly accomplished and insightful expert speaker. So, with this introduction, I request Mehta sir to start with his session. Thank you. Thank you, sir.
Yeah, thank you very much. I don't know your name, but it's a nice introduction. Uh, Thanks a lot.
Thank you. Thank you. Thank you, sir.
Yeah. Uh, so I think how many participants? There are almost 47, 48 participants, 49 perhaps. Oh, it's a good number. So first of all, thank you very much to the organizers for giving me this opportunity to discuss something about what I'm doing in my research. And particularly, it is relevant to the uh, topic or the theme of this STTP. Uh, I will be, dealing with this topic for 1.5 hours. Let us see how much we can go. But I'll try to cover, the topic which is relevant to multi-agent system. Particularly, we are using this in AI-based control. And at the same time, I'm trying to, tell you that, how we developed the concept, of robust sliding mode control for this multi-agent system, which is applied to various systems, like robotic systems, like drones, and in general, you can say autonomous vehicle. So which includes electric vehicles even. Okay. So, we have worked extensively in last 7, 8 years on this topic and developed some novel algorithms for, robust control of this, the electric vehicles, which includes even drones, robots, quadcopters, and many more. Even we have developed algorithm for microgrid. So same concept we have applied to smart grid, microgrid, and many more, I hope I will be justifying the topic and you will enjoy. Definitely, I would say that, control, when we talk about control, it's highly mathematical domain. And so, I have to make it as lucid as possible without, taking much time on mathematics, because it's difficult to understand mathematics immediately within this 1 hour. But I'll tell you the essence of what we have got, in this research, and it has very high impact as far as the algorithms are concerned and applications are concerned. So if you are interested in this particular area, you may directly contact me. Okay, I would be happy to guide you, supervise you. Okay. So let me start my session with I'll start with sharing my presentation. So I'll share my screen. Before I go further, I will show you the. Let me share the entire screen, so I think I can change. Mm. Yeah, is it visible? I think, can anyone just endorse it?
Not yet, sir. It's not yet visible.
I have shared my screen. Not visible.
Not yet, sir.
Just a minute. Let me do it once again.
Okay.
I'll check it with my entire screen itself. I will share. Oh, I think hopefully it is visible. Yeah. Is it visible? No?
No, sir, not yet. Either you can try with the window.
Window, yeah, that would be nice.
You can try with the window.
Let me do it once again. Yeah, window. Yeah.
Whatever open tabs are there, that will be listed over there. You can choose from those windows.
No, there is some issue with the content sharing. Some message I am getting. I don't know. Let me check with individual file, then would be fine. Oh, it is showing this. There is an issue with content sharing. I don't know what is that.
Issue with content sharing.
Yeah, the message I'm getting.
Actually, all rights are being given as a presenter to your ID right now, sir.
I don't know. This message is coming. And once again, I'm trying. Oh, the same message is coming.
Just a minute, sir. I will just make you attendee, and I will just allow you to share it. Just give me 1 second.
Yeah, sure.
Just a minute. Sir, you can check it now. So you can try to share right now. Yes, Mehta sir, just unmute yourself.
Yes, sir, visible.
Yes, now it's visible. Your screen is
Yeah,
visible.
is it visible now?
Yes, sir. Yes, it's visible.
Oh, the screen is visible, right?
Yes,
so I can
entire
see
screen
now.
is visible right now.
Okay, thank you.
Okay.
So I think we can start now.
Yes,
We are
sure. Continue.
on board.
Okay, sir.
Shall I open my camera or keep it open, or shall I stop my camera?
Sir, as you wish.
Okay.
Ah.
So let me begin with this topic. Although the topic is about AI/ML for AI/ML based control for multi-agent system, or you can say the electric vehicle. So in this topic, actually, I will talk about some discrete time sliding mode protocols for leader following consensus of discrete multi-agent system. So here, we will try, to mimic certain bio-inspired systems. Okay. So before I go for the topic and details of this, I'll show you some videos, I think. Okay. And then we will see, we'll discuss on this what you have observed. Okay. So I'm beginning with this video. Please observe it properly.
Hello, sir.
Yeah.
Have you played the video?
Yeah. Is it visible?
Actually, no, sir. No, sir. That's why.
Oh, what is this?
Your screen, entire screen is visible right now, but video, whatever you have played, is not visible.
Okay, I am doing it once again.
One more thing I would like to tell, if that video includes the sound, when you share, just there is one tab, include sound. Just enable that too.
Now is it visible?
Yes, sir.
Okay.
It's fine.
I request all participants to observe this video properly. I'll ask some questions.
Okay, sir.
Bit. My question, to the participants. What have you observed from this video? Hello, am I audible?
Yes, sir. Yes, sir. You're
Yeah.
audible.
So
Dear participants, you can unmute yourself and answer to the question.
yeah, I want to make it interactive because this entire session is based on this video. So I think
Mountain of flying.
yes, very good. It's a bird flock, right? We call it
Yes.
flock. You know, in the evening we usually see such kind of bird flock, right? So what have you observed from this video? What pattern have you observed? You know, what is happening there? Yeah, all the birds follow a path. Very good. I want more answers, you know, because, you know, this is very good. You know, you need to observe the things so that you can do. Anyone else? Hello.
Hello?
Yeah.
Yes, sir. There is a leader and
Yes.
the others are following.
Very
And
good.
there is a particular pattern in which they follow.
Yes. Very good. Excellent. Excellent. Any other observation from any other participant? Okay, let us go ahead. You know, there are few observations which we usually make, you know, in this kind of bird flock, you know, and it is not only the bird flock. There are many such, you know, groups are there. They are working together, you know, like fish cluster. You know, there are certain cluster of fish are there. They make, you know, their own cluster and they act like a one entity, you know. But particularly in this bird flock, you know, they are in certain pattern. You know, there is one leader and all rest of the other birds acts like a follower. But very interesting thing is that the, you know, the last follower does not know what leader is doing. The follower bird just follow the neighborhood bird, you know. So they sense the neighborhood bird's position, velocity, you know, everything they sense from the neighbor only. They don't know what leader is doing. Only the followers which are connected to the leader, they know what his leader is doing, you know. And then rest of these followers, they just sense the position and velocity of the neighbor bird. And then they try to sync in certain pattern, you know. So this is a one observation or two observation, you can say. The third observation you can see that after some time, there is a change in leader, you know. Have you observed that? And then they have a different pattern, you know, new pattern. So that is another, we call it switching kind of pattern, you know. The other observation which you can take that, you know, some birds go out of this pattern on this own will, you know. And then, you know, after some time, some also join, you know, in the pattern. So we call it also switching kind of pattern, you know. So can we use this kind of, you know, decision making of this board particularly for our engineering system? Yes, we can do, provided we can develop some algorithm, you know. That is the base of this research. Okay, I'm showing you another video, you know, just for your interest, you know. I want that, you know, you get interest in my topic, you know. So I'll show you one more video. Is it visible?
Yes, sir. Yes, sir. It's visible.
Yeah, please observe. There is not a good quality, but So you can see that, there is another, flock is there. We call it swarm. Now, can we apply, this kind of pattern? There are in the nature, we will find such, pattern in a, we call it group, in many, entities, like in fish, we can have birds, we can have so many, other. Can we do the same thing for our autonomous vehicle, for making a swarm? Can we have some formation? Can we have some pattern? We may have multiple drones. We can have multiple robots. We can have our own microgrid. So those who are from electrical engineering, they know what is a microgrid. You have a multiple sources. Can we sync them or to follow certain pattern? Can we use this kind of concept for microgrid where the solar is available during daytime and your wind is available in the night time? So this concept we can apply to many applications. There may be missile guidance, multiple missile guidance we can use for satellite navigation. Multiple satellites can be coordinated for single task. Can we do that? And including electric vehicle or autonomous vehicle, can we do it? So my topic, what I am going to discuss, when we want to design a control for not system, but we want to design a controllers for system of systems. It's not about one system. It is a system of multiple systems. Then we can work on this. And it has lots of application, and around the globe the people are doing a lot of research on this topic. And whatever I'll show you, that is our old work. Recently we have included many things in this particular research. We have gone into communication issues, we have gone into cyber physical issues. But today I'll show you the basic thing, what we have done in this. Okay, so I'll begin by my presentation, and you will find very interesting topic. The topic is about protocols for leader following consensus of discrete time multi-agent system. Now this is derived from artificial intelligence. We have a multi-agent system. We call it a system where multiple systems are there, and each system acts like a agent. So let me make it full screen so that it's quite visible to you all. Yeah. So in this presentation, we will discuss what is multi-agent system and what is consensus, and then we will see, why we are going for sliding mode control. It is one of the non-linear control strategy which is widely used nowadays, which is very interesting, robust, and it can take care of uncertainty. Okay, and that is why we have developed these algorithms, for this purpose. Okay, so several algorithms I have developed. I'll show you step by step what we are doing in this, and we'll let you know that what we are doing now, in fact, this current research. Okay. So coming back once again, I have shown you the video also. There is a bird flocking in the sky. You must have observed this thing. Now, similar pattern we are observing in fish schooling, where when number of fishes are there and they act like a one entity, they work in a group, but by communicating with each other. Okay. And there may be a leader, there may not be a leader. Okay. So there can be two kinds of, such kind of group activity, with leader and without leader. Okay. So we are currently dealing with leader following. What does it mean? Mean is that there is a leader knows, what should be the reference and where I have to go. And then rest of the followers will sync with them, they'll synchronize themselves, okay, with the information from the neighbor. Okay. So here each individual system will act like an agent. Okay, and that is the reason we call it multi-agent system. Particularly those who are from computer science background, those who are working in AI ML, they know they in the software engineering they also use this kind of concept called multi-agent system. Okay, so what is a multi-agent system? Is a set of homogeneous or heterogeneous autonomous agents. What is that? Homogeneous in the sense that all the systems are having same dynamics. Here you have seen that all birds are of same entity. They are not different birds. Same birds. But if you are talking about heterogeneous system, then you may have a different system. For example, if I want to sync the quadcopter, so if all quadcopters are of the same dynamics, then I can say it is a homogeneous system, but I may have different types of quadcopters. I may have hexacopter, I may have a quadcopter, I may have wing-based drones, and then I want to synchronize them. Then I would say it's a heterogeneous agents, okay, or heterogeneous system. Now there is a word called agent, and this agent must be smart. So I'll come to that point. What is a smart agent? I'll come to that point. But here, what is important in a multi-agent system that they should be able to communicate with each other, and that is why we will call a smart agent or an intelligent agent. Okay, so it can receive the information from other agents in the neighborhood. Not only that, it can manipulate, it can process those information, and it can share the information with the other neighborhood agents. Okay, and that is why it is called intelligent agent. Okay, so multi-agent system is a combination of multiple interacting intelligent agents. So this agent can be a processor on a system. So suppose I have a multiple drone system. So in each drone, I have a chip or a processor which can communicate with the other system, in the neighborhood. Similarly, I may have a robot. This robot must have the chip which can communicate, which can receive the signal from the neighborhood. Not only that, it can transmit the information, its own information with the other neighborhood agents. Okay, now this can be an autonomous vehicle. Your electric vehicle are made of this thing, because now our autonomous vehicle or electric vehicles are more about processing. It is not about only driving and running the vehicle. Now they are robots. Actually, the autonomous vehicle which are coming in the market, they are more about their processing power. Okay, so we need our electric vehicle to be autonomous, and not only autonomous, they have to be intelligent. Intelligent in the sense, once again, they can communicate with the other agents or other system. Okay, so that is about multi-agent system. Usually in artificial intelligence or machine learning, we use this kind of concept. Now, when this multi-agent system is there, so agent should communicate. Now, why they should communicate, and why they should work together? The reason is that these distributed cooperative controllers can be designed for this kind of system, which has a lot of application. As I mentioned, you may have autonomous system, you can use this in a smart grid, you can use it in a robotic team, biological system, unmanned aerial vehicle, and many more. Even in the satellite navigation, you can use, where satellite can communicate with each other, and they can make certain pattern, certain formation they can do, and they execute certain task, which is given to them. So it's a group activity. Let me tell you, the Western world, including India, we are now working on an army, which can work together and execute certain tasks. Instead of human, now robotic systems are there. They act like an agent, and they have the intelligence. Okay, and they can communicate with each other, and as per the command given to the leader, because leader knows what I'm supposed to do, and rest all will follow the leader, and then they will execute certain task. So Nowadays, we have a formation of these drones also. You might have seen a lot of videos are coming, certain patterns are there. This can be done. Even this can be applied to the missiles, when I'm shooting a lot of multiple missiles, then I can have a leader or I may not have leader, but they can form certain pattern. They can have certain formation and then they execute certain tasks which are assigned to them, So if one missile fails, the other missiles can does the task, In this way, in the military application, they can do. In civilian applications also, it can be used in, as I mentioned, in a microgrid, smart grid. You can have, haptic collaboration, and you may have a highway automation. This can be used, if your electric vehicle is intelligent enough, then it can do its own decision, based on the neighborhood electric vehicles, or the autonomous vehicle. So this is the idea of the cooperative control of multi-agent system. And what we did, we designed certain, algorithms so that it can work collision free and it can execute the task in an autonomous way without human intervention. Okay, so under the idea of cooperation, the agents in multi-agent system share the information with their neighborhood. And as I said in our board flock, they just share the information with the neighbors locally and try to reach an agreement to a certain degree and achieve the objectives. Okay, there are certain algorithms, the computer in artificial intelligence or machine learning, there are certain algorithms which we use that is called consensus, gossip, formation, flocking, rendezvous. These are available. The computer engineers usually use this kind of, while they are developing software, they use such algorithms. Okay, so what is consensus? Consensus says that you have to come to an agreement, okay, with the agents. Okay, this is the agreement among us, and we are in a consensus. You might have observed even in the meeting when you are doing in your department, you have to come to a consensus. Okay, and then you decide, okay, this we will do. Okay, and then you execute the task. The same way in a multi-agent system, you can have a consensus among the different agent, but it's a physical system. It's an intelligent agent. There is algorithm called gossip. I think I need not to tell what is gossip, there is a concept called, bipartite. Bipartite is called, disagreement, It is not necessary that always you be, agree with the other agent. You may have a disagreement, but in a disagreement also, you have to work together, So in AI and machine learning, usually, we use such kind of concept and mathematically we represent this concept, For example, consensus. What is consensus? We have to agree on certain thing, So physical system, when we apply to drones, when we apply to autonomous vehicle, we apply to robotics, or we apply to, any other multi-agent system, it has to come to a certain level. Yes, this is what the consensus. Okay, I'll not talk about other algorithms like formation, flocking, rendezvous. We have developed all such algorithms, okay, in our research. Today, we will talk about consensus only, that how they will come to a consensus multi-agent. Okay, so I'll talk about consensus. There are two types of consensus. There is leaderless consensus, in which simply individual follower agent update its information with the neighborhood agent and achieve an average consensus. While in the second one, there will be a leader following consensus, where you have a leader and the follower just synchronize. You have just seen in the video, the followers have to just adjust with the neighborhood agent. Only leader knows, what I'm supposed to do. But there are certain cases where leader also can be changed. It can be toppled even by the group. And there are cases in a group where even the follower may switch in, may switch out. Okay, these algorithm we have applied to microgrid even, in a microgrid, you have multiple sources, like you have a traditional power, then you have a solar, wind, you have fuel cell, you have battery, and all these they act like an agent, and they, synchronize with each other. They know what my traditional power system is having, how much voltage is it's having, how much frequency it has. So based on voltage level and requirement of the power, they adjust themselves, that how much traditional power will supply to the demand, how much power will be given by solar, wind, fuel cell, and battery. They communicate how much I can deliver, and then they take the decision to supply the demand. Okay. So, in this case, sometimes solar may go out, sometimes wind may go out, sometimes battery may go out, and whenever they are available, they can enter into this group. We call it switching pattern. In a cluster, certain agents can go out from the cluster, certain agents can come into the cluster. And very good research is happening nowadays on this multi-agent and smart grid system, where people have developed, transient free switching. This is where the people have worked. Recently there is one paper in which, they have developed with the same concept for a microgrid, where this switching is happening transient free. There should not be transient while doing this, entering the resource or exiting the resource. Okay. So very beautiful. It's paper. Recently it has come in the literature. Okay, so let us see how many types of consensus of multi-agent systems are available. So it based on certain things like system dynamics. Okay, so which kind of system I have, based on that you may have a consensus. Like you may have a linear system, non-linear system, first order, second order, fractional order, or you may have a higher order system, you may have a stochastic system, and as I said, you may have homogeneous system, you may have heterogeneous system. So, based on system, you can have a consensus study. Like there are certain theories based on algebraic theory, based on graph theory, based on metric theory. Here we are using the graph theory. So graph theory is representing the communication between the agent. So agent-agent communication is there based on your metrics, graph theory. We have studied this graph theory, particular electrical engineering students learned in second year in network theory, graph theory. So based on this graph theory, we tell what kind of communication is there in particular multi-agent system. We may have a directed graph or indirected graph, and based on that, you will be having matrices. We call it Laplacian matrices or Jacobian matrix. You can obtain these matrices we are using in our control, which establish the communication between leader and follower. Okay, I'll come to that point. Okay. Now this consensus we can find in a different time domain also, like continuous time, discrete time system. We are dealing with discrete time system. The reason is that nowadays the communication is in a digital domain. Okay, so our controller should be developed in a digital so that it can be smoothly. Otherwise, if you are having a continuous time and your communication is in discrete time, then you will have to, transform it. So instead of that, we decided, our group decided that we will work on discrete time control algorithms. Okay, so that there won't be any confusion, because your communication data is coming in a digital form, and that directly use, instead of converting into continuous time or analog signal, and then, because our processing is nowadays is digital, so better to develop our algorithm in discrete time. That is the reason. Yeah, any question? Hello.
Hello, please unmute the mic, please. Sorry, sir. Please start.
Sir, just unmute, sir, and start. Sir, unmute, sir.
सरांचा अनम्यूट झाला का सर बघा प्लीज.
Mehta sir, please unmute. Mehta sir, am I audible?
Yes, sir.
Mehta sir.
Sir, you
Somebody
just phone him.
unmuted.
Okay. Okay. You can continue, sir.
Oh, let us see. So, as I said, we are using the graph topology. So we will be using a fixed graph topology and switching type of graph topology. As I said, when agents enter into a communication in a group, then, your graph should be switching type. So I'll come to that point, this is what. Now, type of consensus, there are several consensus. And, there are so many approaches for consensus like event triggered, LQR, sliding mode, fuzzy logic, PID. We can have state feedback, H infinity, Lyapunov, LMI. Out of this, we are using sliding mode control. The reason is that the sliding mode control technology is now matured and it can be now easily adapted to the industrial application. Okay. So with this background, I'm beginning my first, idea that what can be done. So we have tried to develop a consensus algorithm, and we started with a small graph theory. Here you can see one graph. In a graph, I have four, 1, 2, 3, 4 agents. So how agents are communicating, that 1 is communicating with the 2, 2 is communicating with 1 and 3, 3 is communicating with 2 and 4, but 4 is communicating with 3 only. Okay, so based on the graph, the graph is represented by nodes and edges, and based on that, we can have a adjacency matrix. We call it A matrix. So if there is a communication between 1 and 2, there A12 will be 1, but A14 will be 0. You understand? So this graph theory, we know, whenever there is a communication between two agents, so A11 will be 1, A12 will be 1, A13 will be 0, A14 will be 0, because 1 is communicating with the agent 2 only. Okay, it doesn't communicate with other 3 and 4. Okay, similarly, on agent 2, you will see that A21 is 1, A23 is 1, but A24 is 0. So we can develop three matrices. We call it degree matrix, we call it adjacency matrix, and we call it Laplacian matrix. Okay. So this graph theory we already know, we are using this particular mathematics of graph theory for developing our algorithm. Okay. So what we are doing here, we are trying to develop a discrete time sliding mode control protocols for leader following consensus algorithm for a multi-agent system. So that's the idea of today's presentation. So let us see in the first what we have done, and we have what we have done, that let us take one system. So I have taken one system. This is a mathematical representation of my system where the E and F are the system matrices in a state space modeling, and DI is the disturbance. Okay, disturbance is always there. We have to take care of that thing. Okay, so this system is controllable, and that is why we are developing this consensus algorithm. Okay, now you may have a question. Question is that this consensus algorithm is between system to system. What about system control? So based on that, there are two types of controller on each agent. So for example, I have one electric vehicle which has its own control, we call it primary control. So it will take care of all the parameters of its own. But when we talk about secondary controller, it takes care the control between the other agents, like your board. So for example, in a board flow, individual board itself is controlled. But when we talk about entire bird flock, then the other agents, they see what the other bird is doing in the neighborhood, and based on that they adjust, So these controller is a secondary control. So in each bird there are two controls, One is called primary control. So it has to control its own position, velocity, it has to control. And the secondary control is between the different birds. So here we have agents, So between agent and agent, there will be a secondary control, and these secondary controls are distributed, So, distributed, what does it mean? That there is no centralized control. Each individual is having its own control, and then in an overall system, they have to synchronize. So in a centralized control, usually what happens that each bird will share its information to the controller, and then controller will decide what each bird has to do. There should be one entity which is called centralized entity. But in our case, we don't have such centralized entity. There are concept in control called distributed control system, DCS. That is what we are using, but in multi-agent principle, we are using. Okay. So let us take this one system, because, when we want to design the controls, we need mathematics behind it. Okay. So based on this graph theory, we are now writing this system which we call global system. So here you see, here my system, here you see in the first equation it was xi. I means ith agent or the ith system, individual system. Now when I want to combine this all I system and I want to make one system of systems, then I can write using graph theory in this formula, which we call second equation. Okay, you can see that here there is this is a homogeneous discrete multi-agent system, I would say. Okay, so this is not a one system. This is an entire system of systems, which is represented by number 2. Now we are trying to design the controller for this system. We call it multi-agent system. Okay. So what we are doing? So we started our research by designing a sliding mode control for this system of systems. Okay. Now what is a sliding mode control? Sliding mode control is nothing but, it is a state feedback controller which just designed based on sliding surface and a control action. So sliding surface is designed based on what you want from your plant. Okay, so here what we are trying to do, we are trying to adjust the error between I agent and J agent. So based on that, we have written the equation number 5 here, you can see, which tells the error between I agent and J agent. If this error goes to 0, then they both will be sync. Otherwise, there won't be sync. But here you can see that there is leader also. So number 4 equation is for the leader. Leader knows what should be my reference, which I have to follow. And accordingly, in equation 5, we have included the reference also, x0. You see, now these is the xi minus x0 are just neighbor. So if my agent is not connected with the agent, then this AI0 will be 0. This part will not be there. Only xi minus xj will be there. Followers will be there. But whenever there is a leader, the second part in this equation part will come into the picture. Okay. Now, based on this error, we have designed one sliding surface, and based on this sliding surface, this is what sliding surface we have designed. Equation number 9 is for individual agent, and equation 9 is for entire global system. Now for this global system, we have designed a control law. I'll not go into more mathematics on this, but you can see the equation number 16 is the control law which we have derived, which is nothing but sliding mode control. Now we want to apply this thing. So what we did, we tried to simulate it. Okay. So simulation के लिए हमने क्या करना है? We will take one numerical system And then we will see how much consensus is there. We will check the behavior of the system. Okay. As I mentioned, I will not go into more mathematical derivations and other things, but I'll try to give you essence of this. So these control algorithm we developed, and then we check the necessary condition for stability. I will not go into mathematics of this, but it is required. Okay, let us go to the simulation. Okay. So this is about stability. We have talked global stability means in which condition this entire global system will remain in stable. Usually in control engineering, it is very important to check the stability. Okay. So I'll not go into those things, but let us see what we have done. Here you see, we have taken one leader. Leader is 0, number is given. I have taken 3 agents, agent 1, agent 2, agent 3. Now, which kind of system I have? I have taken a second order system, So EI tilde is a second order system. FI is your ABCD matrix, in a state space. So this E represent your A matrix. F represents your B matrix. Okay. You know the state space modeling. X dot is equal to AX plus BU. So these are EI and BI are the individual agent matrix, A matrix and B matrix. Okay. So here you see the communication topology is shown in figure 5, where there is a leader and leader is having the references available. So agent 1, agent 2 and agent 3, they will communicate with each other based on this topology, and they will follow the leader. And you see the leader is communicating with agent 1 and agent 2. You see? So leader is passing its information to follower 1 and follower 2. But follower 3 doesn't have the information. Okay, now based on this topology, I will have a graph theory. You see? I have a D matrix, A matrix. So A matrix is very, very important. A matrix says that there is a communication between 1 and 2. First row, you see, in adjacent matrix, there is a communication between 2 and 3. Okay. So 1 and 2 is having communication, 1 and 3 is having communication. Similarly, second row you see. The second one is having communication with 1 and 3, but not this. Okay. Now this D matrix is just a summation, first row summation, then second row summation, and third row summation. So this is D matrix, we call it degree matrix. Okay. And there is a Laplacian matrix. Now this Laplacian matrix is very, very important. It shows the direction of the communication. Okay. Now this D, A and L is used for deriving the control law, and for sliding mode control, we have to design a sliding surface, which is designed as per 39 equation. Some disturbance is to be given. So we give some disturbance on each individual agent with this cosine function, so that we can check whether it is robust or not, because you have to disturb the system, right? And then you have to check. So you see very beautiful results we have got. So you see blue color line is a leader. So there is a leader, and then agent 1, agent 2 and agent 3 synchronize themselves. Very beautiful results. So this is a very initial results we found, and we got the algorithm. Okay, that multi-agent system works. Like a bird flock, all birds are synchronizing. Okay. So we were very happy, so this result encouraged us to go ahead. So what we thought, and let us see what kind of inputs we are giving, what kind of velocity agents are there. So velocity is also synchronized, but you can see some chattering. The reason is that some chattering is coming because our control effort is a switching type, So the why switching type? Because sliding mode control is a switching type control, like in your refrigerator, it will switch on, off, on, off, on, off. But this is a high frequency switching. So in a sliding mode control, it's a switching signal we are getting. You see in our algorithm, if I'll show you the algorithm which we derived, just coming to that algorithm, there is a switching. You see in 16 number, there is a sign of SK. Sign means switching. It's a relay kind of thing. Okay. So that is what we are getting, relay kind of switching kind of results. Control effort is going to, on each agent is a switching type. And that is why, we are a little bit disappointed. Okay. This should not happen, because we could find there is a chattering, okay, and that is a drawback, okay. But anyway, this is a simulation results. So, we started working, advancing our research. So we found what is this chattering band is there, you see. So we found how much chattering is coming in the band, So we wanted to reduce this band, so that, our control effort will be smooth. It should not be like zigzag kind of thing, switching. We want a smooth control, okay. So we thought, let us do something, okay, and that's why we have gone into second kind of control. So I'll come to that, from some conclude that, we have a topological kind of sliding mode control, but it has a fixed graph topology and it has a chattering, okay. So we have gone, let us see. Now another important thing we wanted, how much time it takes to synchronize. जैसे बर्ड फ्लोक में है, सारे बर्ड एक पैटर्न में कितने टाइम में सिंक हो रहे हैं. So in a physical system, we should have the idea that how much it time for a consensus in a multi-agent system. सारे मेरे एजेंट कितने टाइम में सिंक हो जाएंगे in a pattern, okay, in a communication. So that we found, I'll not go into detail of these mathematics, but with the same control law, we found this much steps will be taken. You see, it's a highly mathematics. You see, 41 equation theorem. So maximum this much time it can take to synchronize. Okay. Now this gives us a very beautiful thing that, we can tell to the world. कि भाई suppose microgrid में आपके पास different sources है, or you want to cater the demand, in how much time they will synchronize each resources. Okay. Now, similarly, you have a drones, let's say, in how much time all these drones will synchronize. Right. That you can tell, So this was very, very important. This we derived. I will not go into derivation of this thing, but we can tell in a finite time, they will synchronize. Now then we have gone into a other kind of reaching law, that is we call power rate reaching law. In this we are trying to reduce the reaching time, and so that we can. Then we have taken a helicopter system. So we have a multiple helicopter systems which are available in my laboratory, and we try to synchronize. Some practical also we wanted to demonstrate, because in simulation it is working. It's okay. But let us see how experimentally we can do. So in this helicopter system, we wanted to synchronize. We have taken 4 such helicopters and we tried to synchronize its angle, in both, So, and so this is the mathematical model. हमने 4 helicopter system लिए और उसी को फिर हमने communication topology में डाले, और then we found out the results, You see all this. These are my simulation results, and we found that all helicopters are synchronized. You see the real world helicopter system. This is our laboratory kind of helicopter system, but in the real world also the same results you can get with the same kind of control logic. So this was a novelty actually. So this novelty we published in journal papers. We published these results that pitch and yaw position can be synchronized, so that you can synchronize all electric vehicles, not only this thing. Okay. And you see these are simulation results for the positions, all helicopters synchronized, and we found that how much steps it is taking, So this much time it takes for synchronization for both first algorithm and second algorithm, and how much chattering it has. So we found that in the second algorithm, the chattering was of order of t square. It got reduced, Tau is the sampling time. So my sampling time is, let's say, 0.01. Then my chattering will reduce by order of tau square, 0.0001. So we could achieve both, synchronization and our effort, which was chattering, that can also be reduced. So you see, these are the results. I'll not go into more detail because of time constraint, because already we have a lot of time has gone. And you see, we have developed such algorithm. We published it in a very good impact journal in a ISA transaction paper, and it was cited by many people. Okay, so I'll not go into more details, but I want to cover the very important thing: switching graph. What is switching graph? As I said in the initial video also, that some birds may leave your your swamp, and some bird may enter. How can we deal with that? So we dealt with switching graph topology. The graph is switching. So what we did, same algorithm we did it, and we try to develop and control law. This is the control law, you see, 47, which we developed mathematically, and then we applied it to a switching graph. So you see here we have taken this topology. See, 0 is a leader, 1, 2, 3, 4, 5 are the agents in graph 1. Okay, so what will happen? There is a communication from agent 0, leader 0 to 1, 2, and 3. But there is no communication between 4 and 5. Like board also you have seen. Now, when this 5, 4, and 5 are entering, let's say, and 1 and 2 are going out from this graph, then my graph will become 0, 5, 4, 3, G2. Now, similarly, let's say 1 is out, 2 is entering, 5 is out, I will have G3. So what will be the change? The change will be in the graph theory. You see? So my graph matrices will change. You see Laplacian matrix, I have Laplacian L1, L2, and L3. You see? Because I have how many systems? I have 6 systems, including leader, and I have 5 followers. So for follower, I have this communication, you see? So this L1, L2, and L3. So adaptively, I have to change this graph, and accordingly, I will have the matrices, and this control law I applied. You see what is happening? Very nicely, whenever there is whatever the follower is there, they will synchronize. Suppose in a graph 1 is there, so graph 1, 1, 2, 3 will synchronize with 0. Similarly, in graph 2, they will synchronize with 5, 4, and 3. Now, this principle, we can use it in microgrid. As I said, when solar power is available, let's say, solar will come in, enter in a microgrid. Whenever there is a wind power is available, it will enter. And in the night time, suppose solar power is not available, solar power will go out of the graph. But ultimately, in a group, in a microgrid, they will cater the demand. Okay, so this is the adaptive kind of thing. We call it switching graph topology, and we got very good results. And then we applied it to a various system, including microgrid. Okay, and that is also happening in fixed time. Okay, so these are some results. We have got it. We have published it in good journal, and very appreciated this work. Okay, so this is about switching type. Okay, now the point is that okay. There was even chattering, even here also you see the chattering is there. You see here, and the chattering is not acceptable to us. Being a control engineer, my effort should be chatter free, and that is why we enhanced our algorithm to a higher order sliding mode protocol. And in this higher order sliding mode control, we were trying to hide the chattering. So what we are doing, we are putting some integrator before the actuator. Whatever the control signal is coming, it will go through an integrator. So what the integrator will do, it will smooth out your relay signal. Whenever relay is there and you put the integrator after your relay, the output of this integrator will be smooth one instead of switching type of signal. So that's what we are doing in this higher order sliding mode control, and we could try to hide the switching. Okay, so this control law we derived based on this higher order sliding mode control. We did the same thing, for this control, and when we found, sorry, we have done even experimental setup with the, I'll show you this video that we could synchronize this robotic arm, which we can apply to electric vehicle, even autonomous vehicle. I'll show you the video if possible. I'll show you. Okay, this we have applied to our drone system also. I'll show you. Okay, so this is there. You see, so many robotic arms are there. Now you can imagine there may be electric vehicle even. Okay, it's because the theme of this STTP is about electric vehicle. So instead of robot, you can have electric vehicle, and we have applied this also, okay, to electric vehicle. Okay, recently we have worked, not published yet. Okay, so this is what we achieved in this. I'll not go into more details of this. You see, synchronization is there between leader and follower. There are 3 followers, FA1, FA2, and FA3. If possible, I can show you the video also, with the what do you call, 2 robotic arms. I think it is there. Okay, I can show you. Can anyone endorse? Yeah, you see the 2 robotic arms are there. I have 4 in fact, but 2 are in my computers. They are virtual. These are physical. Can you see? See, 2 arms are there. And these both systems are different systems, So beautifully, they are communicating. Let me tell you. Just a minute. No, I have some extra class. Okay. So can you see? I have multiple robots like this, which I can synchronize. And let me tell you, each robots are communicating through a communication channel, In my laboratory, we have done it, and we have done very interesting algorithm. We published this work, and we could find very good results on that. Okay, so coming to once again to my presentation. Okay, very quickly I will complete because time is going. These are some, results. Chattering is there, but it is in a 10⁻⁻⁴ level. Okay, so chattering also we eliminated. Okay, and these are some simulation results, and this we have taken. Okay, I'll not go into those things because this is available in the literature. So this is what is happening. We found that in this multi-agent system, each agent is continuously connected with the other agents. Okay, even if that is synchronized. Okay, so we thought, why don't we go for event triggered sliding mode control? Okay, I'll not go into more detail. Let us go to that. Okay, so why event triggered? Okay, so whenever your agent is out of synchronization, at that time only you should take the control effort. Why to waste the energy? Okay, so when we want to optimize the resources, we can go for event triggered kind of sliding control. Okay, so we then develop our algorithm for event triggered. Okay, so what is event? Event is also something like when it is going beyond a certain error, out of this range, then you have to take care of this thing. Otherwise, you need not to do any. You need not to act. Already it is in synchronization. You need not to act. Okay, you have to act only when certain event occur. This you can use in your microgrid, in your autonomous vehicle, everywhere you can use this kind of control algorithm. Okay, so based on this event theory, there is an event theory. We developed the control algorithm. As I said, I'll skip the mathematics derivation, but this is the control law 57, which we have derived, and this we have applied. And you see, we have got very good results for those robotic system which can be applied. See, this is an event triggering instant. So when event will be there, okay? So it is not continuously taking the action, This is an event triggering instance, which we have seen over here in a robotic arm, okay? So there are stage one robotic arm, and second is a second stage. So we developed this thing for robotic arm, okay? You see, very beautiful results we have got. Only instant when it is required to take action, event occurs and it takes control of this. And then we, this followers are following the agents, and we developed. Okay, so coming to this point, we developed so many algorithms, starting with discrete sliding mode control based on Gauss reaching law, then power rate reaching law, then we have gone into switching type of this thing, then we have gone into higher order kind of thing, by putting integrator, and then we have gone into event triggered. Okay, but still there is a problem. because the problem is that in this case, we have considered homogeneous system. But if I have a heterogeneous system, let's say my electric vehicles are of different dynamics. I have, I have a Tesla. Another is my, Jaguar, or I may have BMW. Okay, so these are different, dynamics. Or even drone. I have an electric vehicle of drone, but of different dynamics. So how can I do? So we have gone into the heterogeneous. Okay, I think this will clear you that what we have done. This is the algorithm for heterogeneous system. Okay, and in heterogeneous system also we developed this algorithm. We have taken different kinds of robotic arm, as I shown in my video, that it is synchronizing. Okay, now I'll come to the point, where our electric vehicle or the drone can be done. Okay, so I'll show you some videos which we have applied this algorithm, and then I'll conclude, because already we have gone up to 7:15. Okay, so you see, this is what we have done in our laboratory. We have started with a drone system. You see, we have started with primary control. We are trying to develop one controller for single drone, because your single drone should be controlled. Then you can go for multiple. Is it visible?
Now we are providing trajectory.
The drone is controlled in my laboratory.
Now we get back.
Okay, so this was my first experiment. And then we have gone into leader following kind of thing, you see. So now I will go with
Now drone tracking successfully.
two drones I've taken. One is leader. Where is the leader? The follower is following the leader. See, as the leader moves, follower also moves. Okay. So after doing this, we have gone into 3 drones. You see what is happening. We are going step by step into multiple systems, because it may collide and you may have accident. You see, I'll skip this certain part. You see, I have now 3 drones. Can you see? One of them is a leader, other 2 are the follower. And let me tell you, the drones are communicating with each other. I would say drone is also electric vehicle. Okay, so don't get confused. Why I'm presenting. You see, 3 drones are synchronized at their position. Skip something. See, now drones will move at the leader will move, so follower will also follow it. See, so only leader knows where I am flying. The followers are following the trajectory, what leader has followed. Okay. I'll not go into more details. Okay. Another experiment. Another experiment we also synchronized with the ground vehicle. We have a ground robo. So that also, you see, I have some, one is a drone. The drone is there. So first thing is that as see, when ground vehicle moves, drone also moves. You see, it follows. So it's a leader following algorithm. See, drone is following the leader. Okay. It will come to rest. So, my point is that, the takeaway is that in a multi-agent system, there are several problems are still pending and on which we have worked. In a communication, there may be attack, you may have a delay of information, you may have a packet loss, you may have attack, that is denial of service, jamming of network is there. Then how this swarm can work, how this electric vehicle can work in a swarm, these are some challenges which are open. Of course, people have given some solution. We have also given some solution because, when agent is communicating, the communication channel is becoming very important, So if you are getting delayed information, there may be problem in synchronization. There may be stability issue. There may be some other problems. Okay. So in a critical applications, we cannot take a chance. Okay. So, you can, the takeaway is that now we are working on this cyber physical system, where we are trying to solve the problems of communication channel, So recently we have developed some observers in which if denial of service is there, suppose jamming is there. So the agent and follower are not communicating or follower is not communicating. In that case, how you can take decision and you can keep your group entity and entity in a swarm or uh, in a multi-agent system in a synchronized way. Okay, so these are the few things actually. If you want to see this all this work, you can see. I'll not go into these results, but this will be very important. Here this book was published in 2021, and this is a book which is available and in the Springer, where all these algorithms, its derivations, everything is available. So, and you can see my Google Scholar page where you can find the papers also. And in case if you are interested in this topic and you want some paper, you can write to me at my email ID. Okay. So this is what from my end. I think now it's 7:25 almost in my clock. So let us take some questions and then we can wind up with the in time. Okay.
Participants, any doubt, please ask the questions.
I think it's quite interesting to see our experimental setups,
Yes, sir. Yes.
Yes, sir.
Yeah. Any question? I can see there are 133 participants.
Yes, sir.
See, very important thing. If there is no question, I can share with you. now we are moving for this electric vehicle. We call it autonomous vehicle. All vehicles are now electric. You may be having drone, you may have underwater even. You may have surface vehicles. All are electric vehicles. Now we are going beyond that. Individual controllers are there. Very robust controllers are available. But when we want to, let us say, automated highway system, if we want to develop, particularly in the Western countries, they can do. But in India, it is really difficult. But we can manage somehow, that, we can have intelligence in our electric vehicle. At least we can avoid the collision. You see how many people are dying due to accident. But if we can have certain intelligence in each vehicle, then collision can be avoided. Truck collision, or car to truck collision, or rickshaw collision, bike collision. At least we can avoid those things. So these algorithms are already available, and we need to do what? We have to establish some system where they can communicate with the other vehicle. So if we can put chip on each vehicle, and if we can establish communication nearby vehicles, and if we have a autonomy on that, we can avoid such collision, and we can avoid lots of lives. That's what the idea behind this work actually. So any question? No? I think audience have clearly understood everything, or clearly not understood everything, because there is no question. Or is there anything in the chat? I don't know.
Yes, we understood, sir.
Oh, there are some chats. Okay. The way leader is walking, all other following. Okay. Yes. See, our goal is that to have leader following. But let me tell you, beyond consensus, we are also developing algorithm for bipartite. Bipartite is in the sense, some drone doesn't want to agree with the other drone. Then what to do? So there are so many challenges, like gossip algorithm. How can we apply this gossip algorithm to multi-agent system? Multiple autonomous electric vehicles, So there are so many things, you can do. But ultimately, goal is that this system should work in a group. And this can be applied to multi-missile system, multi-vehicle system, or satellite navigation system. Okay. And this is very interesting topic, because it involves mathematics, it involves communication, it involves control, everything is there. So those who are interested, they may reach out to me. You can see my website, my research, my Google Scholar page, and you can write to me. That's it.
Loss of communication between, can it affect the performance?
Sorry?
Loss of communications between the leader and follower.
Yeah. We have worked on, we call it not loss of communication, we call it packet loss. Okay. So yes. Packet loss means communication happens in a packet. Okay. So now you have two kinds of problem. The packet may get delayed, to reach from follower to follower, or agent leader to follower. Then what to do? So we have developed some algorithm based on Bernoulli principle. So in that case, if we are not getting the packet in time, then we will use the packets which are already available in the stack. So we create some stack of packets, for certain packets. So we see that, can we use those packets, those information for certain amount of time? And if communication established during that time, then we will once again come to the real-time control. Okay, so we have some algorithms on this. Okay. Now, some algorithms we have based on fault also. If some fault occurs, on a sensor or on an actuator, then what to do? So there are several things. which you can take away, very interesting. Yeah, something you were telling.
Sir,
Yeah.
what were the different sensors used, and what was the sampling frequency that was used for digitizing?
Right, very good question. See, sensors, we have there are so many sensors, but here particularly in different system, like a helicopter system, we have encoders. Very simple, yaw and position, pitch angle we measure. When robotics comes, we also have position and velocity by means of encoder. And when drone comes, we have gyroscope and some other proximity sensors are there. And as said, sampling we usually take 1 millisecond.
Thank you, sir.
For hardware, sir, which platform we can use for hardware implementation?
Yeah, for hardware, we have used the Quark software, which will communicate through MATLAB. So when we want to do simulation, MATLAB is enough. In MATLAB, we have our own algorithms we have developed. And for hardware communication from MATLAB itself, it will communicate to the system through a real-time communication software, which we have procured called Quark. You can write in Google also. It's a Canadian software which we have established. So you can have a established. So from MATLAB directly, it will go to the system, and from system directly, it get all the sensor data to my MATLAB. And in MATLAB, I use those data. Controller will be in MATLAB. Only the data which will go to the system through Quark, through MATLAB. So MATLAB will get the data from the sensor through Quark, and whatever the control signal will generate in MATLAB will go to the actuator on the plant through Quark. So in between MATLAB and system, there is a Quark software. It's a real-time system. Like you are in MATLAB, we have DSpace, right? I think those who have worked in DSpace, it is similar to that.
Okay, sir. Thank you.
Yeah, good.
Any other questions for participants? Shall we conclude, sir?
Yes. It's. I think exactly we have.
Yes, sir. 7:31.
Yeah.
Okay.
Let's
On
conclude.
behalf of organizing team, I take this opportunity to propose the vote of thanks for today's FDP session on the topic Intelligent Control System for EV Controller. We are extremely grateful to our distinguished expert, Dr. Axaykumar Mehta, sir, for delivering such an insightful, informative, and technically enriching session. Sir, your depth in explanation of intelligent control strategy, their role in electrical vehicle, information about your switching graph, and the practical perspective on modern EV system have significantly enhanced our understanding of this emerging domain. Your clarity of concept and real world relevant truly made this session valuable for all participants. We sincerely thank you, sir, for sparing your valuable time and sharing your expertise with us. And also our sincere thanks to all the participants for their active involvement, thoughtful interaction, and enthusiastic participation, which made this session lively and meaningful. Once again, thank you all. And my kind request to all participants is to please stay connected. Our next session will begin within 5 minutes. Thank you, sir.
Thank you.
Thank you, sir.
Leave?
Yeah, thank you, sir. I'm Praveen Magdum. Thank you, sir.
Yeah,
Including our
Praveen,
invitation, sir. Thank you.
thank you, Dr. Praveen, for the invitation. And I think hopefully the participants have enjoyed my session. I cannot go for a lot of mathematics because it takes time to understand mathematics, but I have given an essence of what we are doing. Control.
Yes, sir.
So thank you.
Yes, sir. Yes, sir.
Shall I leave?
Yes, sir. Thank you, sir. Yes, sir.
Yes,
Thank
sir.
you. Thank you very much, sir.
Thank you, sir.
Thank you.